Smith. I'm on the Games Technology course and my dissertation is called Implementation of a Cross-Platform Real-Time Fluid Simulation Demonstrating a Model Game Engine. I wanted to get fluids running on mobile devices. That's not something that's been done very often. There's lots of 2D fluids running in parallel on game engines, but very few people have implemented 3D versions. I wanted to do that, so that's basically what we set out to do. This involved writing an external library that would run a fluid simulation and then calling the functions from Unity. So there's some cross-language interaction there. And then developing renderers to turn those back point data from the simulation into something that you can see in a game engine. Over the course of the review, I looked at some of the history of fluid simulation, some detail about the Navier-Stokes equations, which are equations that have become ubiquitous with fluid simulation since the 1800s. I had a look into some other simulations that already exist, some sort of large-scale CUDA developments that are set up by NVIDIA to do big fluid simulations, and I also looked at some small ones that use CPU-only implementations, which is what I was mainly looking for because I wanted this to be a cross-platform project, so it needed to not rely on any platform-specific hardware. Initially, the project was going to use multiple iterations of fluid simulation, and then based on the situation, you would choose which calculations you'd use. So you could do lots of pre-computation, and you wouldn't have to do that computation in real time. Over the course of the literature review, it turned out that wasn't really a good method for developers. It's very difficult to implement changes to that sort of system because you have to rerun all simulations whenever you make any small changes to the game world. So I instead looked at how to take the current particle-based simulations and put that into the engine. So I had a goal, and that was to have the simulation running on each device at a minimum of 30 FPS with some sort of single mesh renderer to make it all look like a lovely single fluid rather than just a series of particles. That was the goal at the start, and you see later in the project that might not have been a realistic goal. That came about through testing and the actual implementation in the end. The library is written in C++, so that was an Xcode bundle. The whole thing was deployed to iOS and Mac devices for now. In theory, it is Windows compatible as well, but I haven't yet built the C++ library to actually run that. I was having some issues with Unity reading that, so focusing on iOS and Mac for now. The library is written in C++, and then Unity runs in C#. That's how they do their scripting. So I created an interop, the layer there that talked between the two languages, management is unmanaged. I set up a demo scene that had a simulation object in there. I had 4 different numbers of particles. I had 500 particles, 2,500 particles, 5,000 particles, and 10,000 particles. And then 2 different renderers. A mesh renderer, which turned all the particles into one solid continuous mesh using a marching cube algorithm to achieve that. And then a particle renderer, which just replaced all of the points with a single mesh. So I ran each number of particles, each renderer across 3 devices, an iPad 4, an iPhone SE, and a MacBook Pro. So that was 30-something tests, I think, in total, with 5 runs for each, averaging the minimum FPS, average FPS, maximum FPS over a 30-second run of the simulation. The project proved that yes, you can make a cross-platform fluid simulation that runs in real time, but there's a reason that nobody does it. Of the many testing I did, only 6 of the possible iterations of it actually made it above 30 FPS with the different renderers and the different particle systems. So it simply proved that you can't run this sort of this amount of processing on CPU currently on mobile devices. You'd be much better off using a GPU where you can do big parallel processing. But of course, to get that cross-platform, that requires a whole load of other problems, like the lack of GPUs on some discrete devices, Further development could be done with using things such as the OpenCL library that Intel provide, because that does some multi-threaded applications with Intel-based devices, and since many of the computers and mobile devices are moving towards Intel. OpenCL has support on a vendor-by-vendor basis, so people can choose whether they want to implement it. So, for example, lots of Intel chips support it. Samsung have included it on their phones. It's included on the iOS with Macs and phones. So that could be one way I could look at optimizing further to make it actually run faster. Other methods include caching and being able to record, like I initially said in my project, recording multiple simulations and then choosing which one to actually use at runtime. That could be an option. All things that simply weren't possible during the time for this project, but I'd like to do in the future. I'm really proud of what it's achieved. I've proven that this can be done. It's just more optimization is needed before it can be deployed on a more widespread level. The best part was actually finally getting particles moving in Unity. That took a long time and a lot of hassle. There were a lot of issues with getting wrapping the C++ language in the C# and getting that actually calling the right function at the right time. Lots of the naming schemes were all messed up because of the way that DLLs and bundles are created. But actually having that was great. And having something showing that points were moving in that simulation that's created externally and the same thing happening in Unity was great.